Dear children, welcome to today's episode on properties and protection of colloids and gold number. In our previous discussions, we have learned a lot about colloidal states of matter, distinction between true solutions, colloids and suspensions, and preparation of colloidal salts and purification of colloidal salts. Let us today discuss the properties of colloids and how we can protect them. Let us also try to find out what gold number is. But before going any further, let me share the learning objectives for today's lesson.
On completion of this topic, learners will be able to know general physical properties of colloidal solutions, understand colligative properties of colloidal solutions, discuss origin of charge on colloidal particles, explain the process of electrophoresis and electro-osmosis, discuss coagulation or flocculation, state Hardy-Schulz rule.
Children, let us first discuss the important properties of colloidal solutions. Let us first take up the general physical properties. The first one is heterogeneity. Colloidal solutions are heterogeneous in nature and consist of two phases, disperse phase and dispersion medium. We will discuss second point, that is visibility of dispersed particles. Although colloidal solutions are heterogeneous in nature, yet the dispersed particles present in them are not visible to the naked eye and they appear homogeneous. I hope you all know the reason by now, that this is because colloidal particles are too small to be visible to the naked eye. Let us now learn about the next property, that is filtrability. Due to very small size, the colloidal particles pass through an ordinary filter paper. However, they can be retained by animal membranes, cellophane membrane and ultrafilters. We next come to the property of stability. Lyophilic salts in general and lyophobic salts in the absence of substantial concentrations of electrolytes are quite stable, and the dispersed particles present in them do not settle down even on keeping. However, on standing for a long time, a few colloidal particles of comparatively larger size may get sedimented slowly. We now come to the last property, that is color. The color of a colloidal solution depends upon the size of colloidal particles present in it. Larger particles absorb the light of longer wavelength and therefore transmit light of shorter wavelength. For example, a silver sol having particles of size 150 nanometer appears violet, whereas that having particles of size 60 nanometer appears orange-yellow. Students, आओ हुन एक नजर colligative properties of colloidal solutions ते पांदे हां. Colloidal solutions exhibit colligative properties, that is lowering of vapor pressure, elevation in boiling point, depression in freezing point and osmotic pressure in the same way as the true solutions of electrolytes and non-electrolytes do. However, the magnitude of these properties for colloidal solutions are much smaller than those obtained for true solutions. This is because colloidal particles exist as aggregates. For a given mass of the substance, the number of colloidal particles present in the colloidal solution of the substance will be much less than the number of particles present in its true solutions. Since a colligative property depends upon the number of particles, a colloidal solution will exhibit much lower value of a colligative property as compared to that exhibited by a true solution having the same mass of the same substance. Colloidal solutions have low values of colligative properties, so it is quite difficult to measure them accurately. However, they exhibit measurable osmotic pressures. The osmotic pressures of colloidal solutions can be measured with a reasonable degree of accuracy. This property is used for the determination of the average molecular masses of the colloids. Let us now discuss about mechanical properties of colloidal solutions. In mechanical properties, let us first discuss about Brownian movement. Colloidal particles present in a colloidal solution exhibit a very important property called Brownian movement. When a colloidal solution is viewed under an ultra microscope, the colloidal particles are seen continuously moving in a zigzag path. The property was discovered by a botanist, Robert Brown, in 1827. He observed that pollen grains in water do not remain at rest but move about continuously and randomly. After the name of the discoverer, the property was named as Brownian movement. It may be defined as follows. The continuous zigzag movement of the colloidal particles in the dispersion medium in a colloidal solution is called Brownian movement. Let us have a look at the Brownian movement shown diagrammatically on the screen. Students, what do you think is the cause of the Brownian movement? Let us now study the cause of Brownian movement. Brownian movement is due to the unequal bombardments of the moving molecules of dispersion medium on colloidal particles. The moving molecules of the dispersion medium continuously attack on colloidal particles from all sides and impart momentum to them. Since the chances of their collisions are unequal, the net driving force on a colloidal particles forces it to move in a particular direction. As the particle moves in that direction, other molecules of the medium again collide with it and the particle changes its direction. The process continues. This results in a random zigzag movement of the colloidal particle. The Brownian movement decreases with an increase in the size of colloidal particle. This is why suspensions do not exhibit this type of movement. Brownian movement plays an important role in imparting stability to a soul. This is because Brownian movement opposes the gravitational forces acting on colloidal particles and prevents them from getting settled down. Let me now ask you a question. What do you think is the significance of the Brownian movement? The answer is, the significance of Brownian movement is that it provides a direct demonstration of ceaseless motion of molecules as postulated by kinetic theory. It counters the force of gravity acting on colloidal particles and hence helps in providing stability to colloidal souls by not allowing them to settle down. Let us now discuss optical properties of colloidal solutions. We will first discuss the Tyndall effect. When an intense converging beam of light is passed through a colloidal solution kept in dark, the path of the beam gets illuminated with a bluish light. This phenomena is called Tyndall effect, and the illuminated path is known as Tyndall cone. The phenomena was first observed by Tyndall in 1869. Let us have a look at the animation to understand it better.
ਇਹ ਚਿੱਤਰ ਟਿੰਡਲ ਇਫੈਕਟ ਨੂੰ ਦਰਸਾਉਂਦਾ ਹੈ। ਡਿਸਪਰਸਡ ਪਾਰਟੀਕਲਸ ਵੱਲੋਂ ਲਾਈਟ ਨੂੰ ਸਕੈਟਰ ਕਰਨ ਨੂੰ ਟਿੰਡਲ ਇਫੈਕਟ ਕਿਹਾ ਜਾਂਦਾ ਹੈ। ਟਰੂ ਸੋਲਿਊਸ਼ਨ ਵਿੱਚ ਮਿਲੇ ਹੋਏ ਕਣ ਇੰਨੇ ਛੋਟੇ ਹੁੰਦੇ ਹਨ ਕਿ ਉਹ ਨਾ ਤਾਂ ਟਿੰਡਲ ਇਫੈਕਟ ਹੀ ਦਰਸਾਉਂਦੇ ਹਨ ਅਤੇ ਨਾ ਹੀ ਫਿਲਟਰੇਸ਼ਨ ਜਾਂ ਸੈਂਟਰੀਫਿਊਗੇਸ਼ਨ ਦੌਰਾਨ ਵੱਖ-ਵੱਖ ਹੁੰਦੇ ਹਨ। ਇਸ ਦਾ ਮਤਲਬ ਇਹ ਹੈ ਕਿ ਇਹ ਨੈਗੇਟਿਵ ਟਿੰਡਲ ਇਫੈਕਟ ਨੂੰ ਦਰਸਾਉਂਦੇ ਹਨ। ਤੁਸੀਂ ਇਸ ਨੂੰ ਸਕਰੀਨ ਤੇ ਵੀ ਵੇਖ ਸਕਦੇ ਹੋ। ਦੂਜੇ ਪਾਸੇ ਕੋਲਾਈਡਲ ਪਾਰਟੀਕਲਸ ਲਾਈਟ ਨੂੰ ਸਕੈਟਰ ਕਰਨ ਲਈ ਕਾਫੀ ਗਿਣਤੀ 'ਚ ਹਨ। ਕੋਲਾਈਡਸ ਦੇ ਕੇਸ ਵਿੱਚ ਟਿੰਡਲ ਕੋਣ ਬਣਦਾ ਹੈ ਅਤੇ ਕੋਲਾਈਡਸ ਪਾਰਟੀਕਲ ਲਾਈਟ ਸਕੈਟਰ ਕਰਦੇ ਹਨ। Since the dimensions of colloidal particles are comparable to the wavelength of ultraviolet and visible radiations, they scatter these radiations and get illuminated. Tyndall observed that the zone of scattered light is much larger than the particle itself. This is why colloidal particles look like bright spots when viewed with a microscope at right angles to the beam of light as shown on screen. Thus, Tyndall effect may be defined as the scattering of light by colloidal particles present in the colloidal solution. Can you now tell me why Tyndall effect is not exhibited by the true solutions? Well, the answer is this is because the particles, that is ions or molecules present in a true solution, are too small to scatter light. Thus, Tyndall effect can be used to distinguish a colloidal solution from a true solution. The phenomenon has also been used to devise an instrument known as ultramicroscope. The instrument is used for the detection of particles of colloidal dimensions. Tyndall effect also establishes the fact that colloidal systems are heterogeneous in nature.
Let us now discuss electrical properties of colloidal solutions. Few important electrical properties of colloidal solutions are as follows: presence of electrical charge on colloidal particles and stability of soles. One of the most important properties of colloidal solutions is that colloidal particles possess a definite type of electrical charge. In a particular colloidal solution, all the colloidal particles carry the same type of charge, while the dispersion medium has an equal but opposite charge. Thus, the charge on colloidal particles is balanced by that of the dispersion medium, and the colloidal solution as a whole is electrically neutral. For example, in a ferric hydroxide sole, the colloidal ferric hydroxide particles are positively charged, while the dispersion medium carries an equal and opposite negative charge. The stability of a colloidal solution is mainly due to the presence of a particular type of charge on all the colloidal particles present in it. Due to the presence of similar and equal charges, the colloidal particles repel one another and are thus unable to combine together to form larger particles. This keeps them dispersed in the medium and the colloidal sole remains stable. This is why sole particles do not settle down even on standing for a long time. Based on the nature of charge, the colloidal soles may be classified as positively charged and negatively charged soles. Some common examples of these soles are positively charged soles. Metallic hydroxide soles, for example, FeOH3, AlOH3, CrOH3, etc., TiO2 sole, hemoglobin, soles of basic dyes such as methylene blue, etc. Negatively charged soles. Metal soles, for example, gold, silver, copper, platinum, etc. soles. Metal sulfide soles, for example, As2S3, CdS, etc. soles. Starch sole, soles of acid dyes such as Congo red, etc. Now that we have discussed so much, let us now discuss the origin of charge on colloidal particles. There are several views regarding the origin of charge on colloidal particles. According to these views, colloidal particles acquire charge due to the following reasons: due to dissociation of the adsorbed molecular electrolytes. Colloidal particles have a strong tendency to adsorb reactant or product molecules. The molecules thus adsorbed on the surface of colloidal particles may undergo dissociation or ionization and may impart charge to them. For example, during the preparation of sulfide soles, As2S3 sole, H2S molecules get adsorbed on colloidal particles. H2S molecules thus adsorb, undergo ionization and release hydrogen ions into the medium. Consequently, colloidal particles are left with negative charge. Due to the dissociation of molecules forming colloidal aggregates, the molecules responsible for the formation of aggregates of colloidal dimensions may themselves undergo dissociation or ionization, resulting in the development of charge on the colloidal particles. formed by their aggregation. For example, the soap molecules dissociate to give RCOO negative and Na positive ions. RCOO negative ions aggregate together to form micelles which carry negative charge as explained earlier. Due to preferential adsorption of ions from solutions, the colloidal particles have a tendency to preferentially adsorb a particular type of ions from the solution. A colloidal particle usually adsorbs those ions which are in excess and are common to its own lattice. This preferential adsorption of a particular type of ions imparts a particular type of charge to colloidal particles. For example, when a ferric hydroxide sol is prepared by the hydrolysis of ferric chloride in warm water, the colloidal particles of FeOH3 formed have a tendency to adsorb preferentially the ferric ions present in the solution. This is because ferric ions are common to the lattice of FeOH3 particle. The ferric ions thus adsorb impart positive charge to the colloidal particles present in the sol. Have a look at the equation on the screen. Let us now discuss electrical properties of colloidal solutions. During the preparation of silver chloride sol, using excess of potassium chloride solution, the chloride ions are preferentially adsorbed and the colloidal particles acquire negative charge. However, if an excess of AgNO3 is used, silver ions get preferentially adsorbed and the colloidal particles acquire positive charge. Let us now discuss the second method, that is electrophoresis. Have a look at the diagram present on the screen. There are two figures. The first one is a case of before electrophoresis. Due to the presence of a particular type of electrical charge, the colloidal particles present in a colloidal dispersion move towards a particular electrode under the influence of an electric field. The direction of movement of the colloidal particles is decided by the nature of charge present on them. If the colloidal particles carry positive charge, then they move towards cathode when subjected to an electric field and vice versa. The phenomena is called electrophoresis and may be defined as follows. The movement of colloidal particles towards a particular electrode under the influence of an electric field is called electrophoresis. The phenomena of electrophoresis clearly indicates that the colloidal particles carry a particular type of charge. The property can be used to find the nature of charge carried by colloidal particles in a colloidal dispersion.
Electrophoresis. Electrophoresis is carried out by placing the colloidal solution in a U-tube which is fitted with platinum electrodes. When electric current is passed, the charged colloidal particles move towards the oppositely charged electrode. A colloidal sol of As2S3 which is negatively charged will move towards the anode when placed in an electric field. Electrophoresis is an important phenomenon and finds several applications in industry.
We will now discuss about the third electrical property of colloidal solutions, that is electroosmosis. When the movement of colloidal particles under the influence of the applied electric field is checked with the help of a suitable membrane, which is a semi-permeable membrane, the dispersion medium moves in a direction opposite to the direction in which the colloidal particles would have otherwise moved. This phenomena is called electroosmosis and may be defined as follows. The movement of dispersion medium under the influence of an electric field in the situation when the movement of colloidal particles is prevented with the help of a suitable membrane is called electroosmosis.
Electroosmosis can be demonstrated with the help of the apparatus shown on the screen. The colloidal solution is placed between two partitions made by semi-permeable membranes. The outer compartments consisting of platinum electrodes and side tubes are filled with water. On passing electric current, water level begins to rise in one of the side tubes and falls in the other. The phenomenon can be explained as follows. We have already seen that colloidal particles and dispersion medium carry charges which are equal but opposite in nature. Under the influence of an electric field, both have a tendency to move towards the oppositely charged electrodes. Semi-permeable membranes do not allow the passage of colloidal particles. However, dispersion medium can pass through them. Therefore, during electroosmosis, colloidal particles are checked and it is the dispersion medium that moves towards the oppositely charged electrodes.
Let us now learn about coagulation or flocculation. The stability of a sol is due to the charge present on the colloidal particles. Due to similar charges, colloidal particles repel one another and are unable to combine together to form larger particles. However, if the charge on colloidal particles is destroyed, they are free to come nearer and grow in size. When the particles become sufficiently large, they get precipitated. This phenomena is termed as coagulation or flocculation. The coagulation of colloidal solution can be achieved by the addition of an electrolyte. It is to be noted that a small amount of electrolyte is necessary for the stability of a sol because the ions of the electrolyte get absorbed on colloidal particles and impart them some charge. However, when an electrolyte is added in a substantial amount, the positively charged ions of the electrolyte neutralize the charge on colloidal particles and compel the sol to get coagulated. Coagulation may be defined as follows. The phenomena involving the precipitation of a colloidal solution on addition of an electrolyte is called coagulation or flocculation. Let us study a rule to find out the coagulation capacity of an electrolyte. This can be governed by a rule which is Hardy-Schulz rule. The coagulation capacity of an electrolyte depends upon the valence of ion responsible for causing coagulation. As we have seen a little while before, the ion responsible for causing coagulation is the one which carries charge opposite to that present on colloidal particles. For example, a positively charged sol gets coagulated by the negatively charged ions of the added electrolyte. From a study of the coagulation behavior of various electrolytes towards a particular sol, Hardy and Schulz suggested a general rule known as Hardy-Schulz rule. This rule can be stated as follows. The greater is the valence of the oppositely charged ion of the electrolyte added to a colloidal solution, the faster is the coagulation of the colloidal solution. Thus, higher the charge on oppositely charged ion, greater is its coagulating power. For example, the coagulation power of different cations for coagulating a negatively charged sol of As2S3 follow the order as shown on the screen. Similarly, for the coagulation of a positively charged sol such as FeOH3, the coagulating power of different anions follows the order as shown on the screen. Do you know what is flocculation value? Let's define it. The coagulating power of an electrolyte is usually expressed in terms of its flocculation value, which may be defined as follows. The minimum concentration of an electrolyte required to cause the coagulation of a sol is called the flocculation value of the electrolyte. It is expressed in millimoles per liter. The flocculation values in millimoles per liter for the coagulation of negatively charged As2S3 sol and positively charged FeOH3 sol can be shown in the form of a table which you can see on the screen.
The flocculation values of some common negatively charged sol and the positive charged sol are shown in the table. It is to be noted that a smaller flocculation value indicates the greater coagulation power of the electrolytes. Thus, coagulating power is proportional to 1 upon flocculation value.
Children, let us now learn about protective colloids and gold number. Lyophobic sols such as those of metals, for example, gold, silver, platinum, represented as Au, Ag, Pt, etc. are not very stable in the sense that they get easily coagulated or precipitated in the presence of an electrolyte. This poses a big problem in their storage and usage. Contrary to this, lyophilic sols are much more stable and do not get coagulated easily under similar conditions. Then how do we protect the lyophobic sols from being coagulated? Let's discuss in detail. It has been observed that in the presence of certain lyophilic colloids such as gum arabic, gelatin, starch, etc., the hydrophobic sols acquire greater stability towards coagulation. That is, they get protected and do not get coagulated easily when an electrolyte is added. The process of protecting a lyophobic sol from being coagulated or precipitated on addition of an electrolyte by the use of a lyophilic colloids is called protection, and the lyophilic colloid used for purpose is called a protective colloid. For example, the addition of gelatin, which is a lyophilic colloid, to a gold sol, which is a lyophobic sol, protects the lyophobic sol from being coagulated on addition of sodium chloride solution. Can you predict the mechanism of the protection? Let's have a look at the animation.
This animation depicts the protective action of lyophilic colloid particles. The exact mechanism of protection is not very clearly understood. However, it is believed that the lyophilic colloid particles get adsorbed on the surface of the colloid particles present in the lyophobic sol. The adsorbed lyophilic particles thus form an envelope around the lyophobic sol particles and protect them from the action of electrolytes.
Children, let's now discuss what is gold number. Let's try to understand it. The protective power a lyophilic colloid is usually expressed in terms of a number called gold number, introduced by Zsigmondy in 1901. It may be defined as follows. The gold number of a protective colloid is its minimum amount in milligrams, which is just sufficient to prevent the coagulation of 10 milliliter of a gold sol on the addition of 1 milliliter of 10% sodium chloride solution.
The given table shows gold number of some protective colloids. It is to be noted that the smaller the value of gold number, the greater is the protective power of the protective colloid.
Children, we have studied today about the general physical properties of a colloidal solutions. We also studied about colligative properties of colloidal solutions, in which we discussed in detail about the mechanical, optical and the electrical properties of colloidal solutions. We also discussed the origin of charge on the colloidal particles due to dissociation of the adsorbed molecular electrolytes. Due to dissociation of molecules and due to preferential adsorption of the ions from solutions. Lastly, we discussed about electrophoresis, electro-osmosis, coagulation and defined gold number and the protective colloids. So now we come to the end of today's topic. Here's a quick test for you to find out how much you have actually absorbed by solving a problem. Let's start with this question. The coagulation of 100 milliliter of colloidal sol of gold is completely prevented by addition of a 0.25 grams of starch to it before adding 1 milliliter of 10% NaCl solution. Find out the gold number of starch. Now, let us try to find out the solution for this. Starch added to 100 milliliter of gold sol to completely prevent coagulation by 1 milliliter of 10% NaCl sol is equal to 0.25 grams is equal to 250 milligram. Starch required to be added to 10 milliliter of gold sol to completely prevent coagulation by 1 milliliter of 10% NaCl sol is equal to 25. By definition, gold number of starch is equal to 25. My next question is, what modification can you suggest to Hardy-Schulz law? Answer is, it could be expressed in terms of polarizing powers and polarizability of an ion, which could give an exact view of its coagulating power. Polarizing power is a ratio of charge to radii of an ion. If this is calculated, a clear picture of the strength of the ion can be formed, as it would compare both the effect happening due to charge as well as size, just like free energy, which does that on enthalpy and entropy. Well done, students. So, I hope that you all have enjoyed today's lesson on properties, protection of colloids and gold number. Thank you, students, for the attention you have paid in understanding these concepts. I hope you have enjoyed the lesson as much as I have enjoyed. Looking forward to the next class. See you then. Bye-bye.